Alright, so let's start. Okay. I hope my screen is visible. Is it? Can you unmute yourself and can you confirm whether my screen is visible? Hello? Looks like people have not joined today. So anyway, I will be starting with this week's content. I'll be solving the problems myself. If anyone wants to look at today's session, they can go through the YouTube lecture that I will be uploading. So alright, I will be sharing the screen now. Yeah. Sorry. Okay, so alright, so this course is Basic Electrical Circuits. It's offered by NPTEL this semester, and it is taken by the instructor Dr. Ankush Sharma. He is from the Department of Electrical Engineering, IIT Kanpur. He is a professor. I will I am the tutor for this course. I will be solving sample problems for in the sessions that are conducted for this course, and this is today's one such session. So my name is Mayank Anupam. And I am a PhD student and a PMRF scholar. I also belong from the same IIT, which is IIT Kanpur, and I am from Department of Electrical Engineering. Okay, fine. So moving ahead. In week 4, all the students in week 4, the instructor discussed about first order circuits, right? So he talked about first order circuits. What are first order circuits, by the way? So all first order circuits are all the circuits whose differential equations are of the first order. Basically, when you write a circuit, when you have a given circuit, and you write the voltage current equation for it, you will get some differential equations. So if it is a simple resistive network, you will not get any differential term, by the way, but for that case we say that the order of the system is 0, because if you have only IR, let me explain what I am trying to say. So suppose you have only a single voltage source, then you have a resistor R1 and a resistor R2, and suppose you are interested in writing the voltage at this node VO in terms of voltage at this node Vin. What will this be? VO is equal to, it's a simple resistive divider, right? So VO is equal to Vin times R2 divided by R1 plus R2, isn't it? So it can be rewritten in this form: VO times R1 plus R2 divided by R2 is equal to Vin. Or in other words, you see, VO into R1 plus R2 divided by R2 minus Vin is equal to 0. You see that this is also an equation, right? This right here is an equation. But what is the order of this equation? It can be said that it is also a differential equation. But you see that there is no derivative term in this particular equation. So we say that such a system, such an equation is zeroth order differential equation, right? So you might remember that nth order differential equation looks something of this kind. Let's say your variable of interest is y and you're differentiating it with respect to x. So this is how it should look: dn minus 1 y divided by dxn minus 1 plus dot 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 dy divided by dx is equal to plus some constant a is equal to 0. So this is a general nth order differential equation. If in this case n is 0, then basically you will get what? Some constant is equal to 0, which is what we are getting here. Some constant is equal to 0. So this is a 0th order system. So this case here, it becomes a 0th order differential, sorry, 0th order hold on a second. Hi Farha. So you are a bit late, right? So I have started my screen sharing already. I've started teaching. I've started discussing this week's concept. So you can look at it once. If you have any doubt, you can interrupt me in between. Right. So is this visible, Farha? Can you confirm? Hello.
Yes, sir.
Is this screen visible?
Yes, sir. Yes, sir.
Yeah, fine. So I was just talking about the first order circuits. So in week 4 you have been studying first order circuits, right? Sorry, in week 5. This is week 5, by the way. Oh, I am sorry. This is week 5, not week 4. Okay, sorry. Yeah. So this is week 5, and you have been studying first order circuits. So I was just talking about what are first order circuits, by the way. So can you tell me what are first order circuits? Can you unmute yourself and tell me what are first order circuits? Hello? Okay. Fine. So yeah, so I was discussing about this first order circuit. So this is what? In this case, this is a 0th order circuit, because the response in this case, the differential equation which is governing the system, the circuit in this case is 0th order. So I guess you have an idea of how do we find out the order of a circuit. Now that being said, what are first order circuits? So first order circuits are those circuits in which you have only and exactly one memory element. So suppose this is as an example, this is right. So what do I mean by a memory element? So in general, capacitors, inductors, these are two memory elements. Why do I say that these are two memory elements? It's because you remember that capacitors, for a capacitor, the voltage V and the current I, these are related in this fashion, right? So I is equal to C dV by dt, correct? Similarly, so if you want to write the voltage across it as a function of time, what you will do? You will write it to be equal to 1 over C integral of I dt, and t will be there will be appropriate limits right here, and because you are integrating it within some limits, right? So this will be some t naught to tf, right? And when you do that, you can see that the value of this voltage across the capacitor is not only a function of suppose I want to find out now the voltage at tf. Okay, now you can clearly see that voltage at t final, tf, is also dependent upon the current, this current, which was, so let me repeat myself. You can see that in this case, the voltage at time tf is dependent upon the current at time tf, as well as all the previous values from starting from t naught, right? So in this case, that is why you say that this particular element has memory, because you see what is indeed meant by memory. Memory means what? You are remembering the past, right? So that is memory. So here also the capacitor also remembers the past. So the voltage across it is not only a function of the instantaneous time, instantaneous value of current, but also the previous values of current. So that is why the capacitor is a memory element. Similarly, an inductor is also a memory element. So you can find out the reasoning for that. You can guess the reasoning for that. If you have doubt, if you have some doubt, you can ask me later. Fine. So now that being said, let me remove this first. So this week you learnt about first order RC circuit. Yeah, so I was talking about the first order circuit. So simple first order circuit. This is a first order circuit. Why? Because in this case, you see, the differential equation that will be governing this particular circuit will be first order in nature. There will be a term of this kind, like so let's write. So this is the current, right? I. So this is the voltage V naught. So what is V naught? V naught is equal to CT. Sorry. Okay. Yeah. So let's write KVL around it. So it will be VI minus IR, minus V naught is equal to 0, right? And what is this I, by the way? This I is equal to C dV naught by dt. So let's replace that. So this will become VI minus C dV naught by dt minus V naught is equal to 0. So you see, this is the first order differential equation, isn't it? You see the variable of interest V naught, it's a first order differential equation in that, isn't it? So that is why we say that this kind of circuit is a first order circuit, because the differential equation that we will be getting for this particular circuit will be first order in general. Similarly, a similar analysis can be done for RL circuits also, and you will see that this will again be first order differential equation that you will be getting. So we also talked about source free and forced response. So what was source free response of first order circuits? So first order circuit was of this kind, isn't it? So this you see, this is R, this is C. So in this case, here you can see that there is a voltage source, an external independent source that I have connected here, which is driving this particular circuit, RC network, right? Here you see that there is nothing driving this circuit. So and only thing that will be causing a current to flow will be the initial value of voltage that is stored on this capacitor. So if you charge this capacitor to a certain value of voltage and you leave it in this particular arrangement, then you will see that there is a current which will be flowing in this case. So but you have not connected any independent source in this case. So that is why this is source free, and since you have connected an independent source here, this becomes forced response, forced circuit. It is forced because the currents and all the response in this case is forced by an independent voltage source here, or any independent current source, whatever. Fine. You also studied at the end of this particular week, you studied about the second order source free RLC circuits. So we will not be touching that this week in this session. We'll be covering this part in the next week's session. So fine. So we will be touching the first two parts today. Okay. So yeah, so I will encourage. So this is a particular circuit. I have this is one question. So in this case, we have to find out the time constant of this particular circuit, of this particular network. This is an RC circuit, right? You can see that there is a voltage source, but instead of if you ignore this for a moment, you can see that this is only a capacitor and series capacitor in some which is connected in some fashion with the resistors. So there are only resistors and only one capacitor, right? So it can be said that it's only a first order circuit. Why did I say that it is a first order circuit? It is because there is only one capacitor. As I said that the order of the circuit will be at most equal to the number of memory elements in the circuit. So in this case, the number of memory element which is a capacitor is only one, right? So in this case, the order of the circuit is only one. All the other elements, resistor, and this voltage source, they are not memory elements, right? Okay, so this is a first order circuit. So I have asked in this question to find the time constant of this particular RC network. So I have already given the answer here, 30 milliseconds. But I would encourage you all to pause the video for a moment and look at it and try to find out what is the order of this circuit, and try to do that. Okay, I hope that all of you have tried it. So fine. So let me now share my screen, and let me go to another screen now. Okay. Yeah. Fine. So I hope my screen is visible to you all. Okay, fine. Let's solve this particular question. So I have asked you to find the time constant of this particular circuit, right? This is the circuit here, and I asked you to find the time constant. So what should you do in order to find the time constant? So this was covered earlier in the week. So if you have to find the time constant of a first order RC network, you have to first see where the capacitor is. So there is a capacitor here, right? And in that you have to find the Thevenin resistance in between the terminals where the capacitor is connected. I am saying capacitor because in this case we have capacitor. If there is an inductor, then you will be removing that inductor, and you will be seeing you will be finding the Thevenin resistance, which is seen across the terminals where the inductor is connected. So in this case we have a capacitor, so we have to find the Thevenin resistance, which is here RTH, between these two terminals, isn't it? Fine. So let me erase this. It's messy here. Okay, fine. So for simplicity, I will assume that this particular node here is my reference or ground. Fine. Now how do I find the Thevenin resistance in this case? So my circuit, for finding Thevenin resistance between, let's say this is terminal A and this is terminal B. So for so I will write it here. To find the time constant, we have to, okay, hold on a second. Yeah, so hi Raghav. So are you able to see my screen? Hi Raghav, can you unmute yourself and confirm please if you are able to see my screen?
Yeah, I can see you. Please go ahead.
Oh
I'm
yeah.
from NPT.
Oh, sorry.
That's okay.
Yeah, so okay, so I was saying that we have to find the time constant in this particular circuit, right? Okay, hold on. Okay, yeah. So how do we find it? So as I was saying that to find the time constant, we have to first find out the Thevenin resistance, right? Thevenin resistance across terminals A and B, right? So how do you do that? So Avinash, can you unmute yourself and tell me how to do this? How should we proceed in this case? How do we find the Thevenin resistance across this terminal A and B? Okay, fine. Okay, so I will be doing it. Try to follow it. If you have any doubt, you can ask me, interrupt me in between, and you can ask me. Yeah, so for finding the equivalent resistance, we have to do the following. We have to first short all the independent source. We have to first desensitize all the independent sources which is inside this particular circuit. So you can see there is only one independent source, which is a 50 volt voltage source. So we have to short this particular voltage source, right? And we also have to remove this capacitor here, because we are trying to find the Thevenin resistance across these two terminals. So my circuit, how will my circuit be modified in this case? It will be like this, right? So this is a 120 ohm resistance, this is an 80 ohm resistance, fine. This is a 12 ohm resistance, this is terminal A, and this is connected here, this is terminal A, this is B, and there is a ground here. We have assumed there is a reference here, right? Fine. So now what do we do? This is step 1. Now step 2, we have to find out the equivalent resistance, right? R equivalent here. So what is the equivalent resistance here? You see that this 120 ohm and this 80 ohm, they are in parallel, right? So this particular terminal is shared for both, and this particular terminal is also common for both of these. So these two are in parallel. So what will be equivalent resistance? It will be, for this case, 120 times 80 divided by 120 plus 80, which is 120 times 80 divided by 200. This and this gone, this and this gone, 2 4s are 8, it becomes 48 ohms, right? Now how will my circuit be modified in after this particular transformation, which is in parallel? So my circuit will become like this. So this becomes 48 ohms, and there is a 12 ohm resistance here. This will be like this. This is A, so this is B, and this is reference here. So you can see that between A and B, these two resistors, they are in series, right? They are in series. So my new equivalent resistance becomes how much? It becomes equal to 48 plus 12 ohms. So this becomes 60 ohms, isn't it? So so we have found out what is the R equivalent, and which is this was equal to the Thevenin resistance. This is equal to 60 ohms in this case. Fine. So we have found out what is the Thevenin resistance, which is 60 ohms. Now how do I find out the the time constant of this network? So you can see, you remember that the time constant, step 3, time constant is equal to R Thevenin times C, right? So in this case, what is Thevenin, R Thevenin? It's 60 ohms into, what is the capacitance C? It's 0.5 millihenry, right? So let's write that here. It's 0.5 milli. So how much will this become? 30 millisecond. Right. So you can see that in this case the time constant, which is also represented by tau, is equal to 30 millisecond, isn't it? So let's see whether that is indeed correct or not. The answer that I had shown in my slides. Oh, it is here. Yeah, so you can see that the answer is indeed 30 milliseconds, and which is what we are getting here, right? Fine. So any doubt in this? Did you find any difficulty in this particular example that I showed? You can unmute yourself and you can say if you have any doubt, or if you are clear then you can say that yeah, I was clear. Okay, fine. So no response will be counted as no doubt. Fine. So let's go ahead now. Now this is the second question that I had given. I wanted to discuss. So in this case, I wanted to find out the response of the circuit. So what happens in this case is that this particular switch here, I hope my pointer is visible. So this particular switch here, it changes its position as at time t is equal to 0. So before time t is equal to 0, and before that this switch was connected between this, so between A and the output, and when after time t is equal to 0, the switch changed its position to B. Okay, so I wanted to so basically this is a question: what will be the voltage V as time t is equal to as time is for time greater than 0? That is my question. So the question is also written here. The switch in figure moves instantaneously from A to B at time t is equal to 0. So find the voltage V for time t greater than 0. So how should I proceed in this case? Any help that you can give me? So okay, so the second question is here. So we want to find out, so we want to find out what will happen to the voltage V here as time t is equal to 0, as time t is greater than 0. So the question was, find V naught of t or t greater than 0. So before t, so let's now try this question. So before t equal to 0, that is for t less than 0, what was the condition? The circuit was like this. Yeah, so it will be it is understood that this point will be counted as the reference. Okay, fine. So this was the circuit was like this, 5 kilo ohm resistance, and this is A. This was directly connected with the capacitor here. This is 10 microfarad. Fine. So this was the condition before the switch changed its position, right? Before time t is equal to 0. So it is assumed in this question. Not assumed, but you can say that this condition was remaining for a very long time, so that the steady state has been achieved in this particular circuit. So what is the voltage in that case at this point? Basically I am trying to ask V is equal to what? So you remember that in steady state no current can flow across the capacitor, right? In a DC steady state, current flowing through the capacitor is 0. Fine. So in this case you can say that the current is 0, since in this branch the current is 0. So there can be no voltage drop across this 5 kilo ohm resistance, right? So whatever voltage is at this point, the same voltage should be there at this point also, because if there is a mismatch in the voltage at this point and this point, so there will be a net voltage developed across this 5 kilo ohm resistor, and that net voltage will cause a net current to flow through this resistor, right? So but that is not possible in DC steady state. So hence we can say that the voltage here and the voltage at this point are both same. So voltage at this point is what? The voltage at this particular node, let's say it's V in. So what is V in? So V in is equal to 40 volt. You see that there is a voltage source connected between V in and the reference. So this is 40 volt. The same voltage will be appearing here also. So right, so V in this case, the V here will be equal to 40 volts. So we can say, so why did I do this? So now voltage V t for time t less than 0 is equal to 40 volts, right? Now we have to find out the voltage after t is equal after t greater than 0, right? For t greater than 0. So second part, yeah, for the second. Okay, so people who have joined just now, so I am discussing this particular question. Okay, so I want to, in this let me explain you the question here. Do you have any doubt? Okay, fine. So I was discussing this question, so let me explain the question first. The question is that in this particular case there is a voltage source. You can see this network, right? So there is a switch here, right here. I don't know whether my cursor is visible or not. So can you see my cursor here as I am moving it with my mouse? Can any one of you unmute yourself and just confirm? Can you see my cursor here? Okay, fine, thank you. Fine. So basically, you can see that there is a switch here, and this switch is changing its position from A to B, right? So before time t is equal to 0, that is for all time less than 0, so this switch was connected with A, okay, and just at time t is equal to 0, it's changed its position to B. So I am trying to find out what happens to this voltage V here for time greater than 0. So this is the question. So find V naught t. This is V naught. This is not V naught. This is V. Okay. So this voltage here. Find this voltage for time t greater than 0. Fine. The question is clear now, right? So for that I started in this manner. Is that I first have to find out what is the voltage, initial voltage that is stored on this capacitor, right? So when this switch is connected at A, so this is the condition, right? This is the particular condition. This 40 volt voltage source in series with this resistance is connected with this particular capacitor, right? This is the condition for time t less than 0. Okay. So for that case, I first have to find out what happens to this voltage, because in that case you can all agree that this voltage, this capacitor will be charged. In that case there will be some initial voltage which will be developed here, and when this capacitor, when this switch, it flips its position to B, at that time there will be only capacitor and resistor which will be connected here, and you can imagine, you can expect that this particular voltage will start to discharge. This capacitor will start to discharge, isn't it? So in order to find out the discharge voltage, we first have to find out what voltage was there initially on this capacitor, right? Is this understood? Can anyone of you please comment or say something here? Okay, fine. So I guess if no one is saying that, that means everyone is clear with this. Fine. So yeah, so first I found out what is the initial voltage which is developed on this capacitor, right? So for that I saw what is this is the particular network, right? And I said that okay, at steady state, so yeah, so this is the network, right? So in steady state, in DC steady state, the current flowing through this capacitor will become 0. So that is why the voltage here should be equal to the voltage here. That is why this voltage here V, that the capacitor voltage will be initially equal to 40 volts. Now in the second part, my, let me bring down this particular guy so that easier to track. Yeah, okay, fine. So by the way, this is my reference. Okay, now for my second part, my circuit becomes like this. So this is 2 kilo ohm resistance and this is a capacitor here. This is the voltage V and the capacitor is how much? 10 microfarad. Okay, and this is my circuit for the second situation, basically for time t greater than 0, right? And this voltage initially V of 0 is equal to how much? It is equal to 40 volts, right? With the same sign. So this voltage V of 0 is 40 volt. So now I have to find out what happens to this voltage as time goes along. So for that we can we remember that for any first order circuit, for any first order RC circuit which is charged to a particular, so let me remind you. So if I have a capacitor like this, if I have a resistor in this case RC, and suppose capacitor is charged with some initial voltage V0, in this case this is the example, classic example of source free RC circuit, isn't it? So how is the response of this source free RC circuit? V0 of t, sorry, not V0 but V of t, which is the voltage here, voltage V of t will be some V0 times exponential of minus t over RC, right? You remember this. So this is the response of a first order RC circuit which is source free, right? Which is basically excited due to the initial condition on the capacitor. Then this is the particular response. So in this case also, in our case also, we have a capacitor like this, C is equal to 10 microfarad, and we have a resistor here which is equal to how much? I guess it is equal to 2 kilo ohms, right? Am I right? Yeah, it is right. Yes, this is 2 kilo ohms. So what will be the response in this case? And what is V0, by the way? V0 is equal to 40 volts. So what is the response? V of t will be equal to 40 times exponential of minus t by 2 kilo ohms times 10 microfarad, right? So this becomes how much? 2 kilo times 20 micro, what is the value? It's 20 milli, right? So it becomes 40 exponential minus t by 20 milli, isn't it? Yeah. So now, and what is 1 by 20 milli? So it can be simplified and written in this manner. This is 40 exponential minus t into 1000 divided by 20, and this becomes 50, right? So it is 40 exponential minus 50 t volts, right, for t greater than 0. So is there any doubt in this solution? So is there any doubt? The people who are present, do you have any doubt in this particular solution? Okay, so no response will be counted as no doubt. So fine. So now let's see whether this is indeed the answer. So the answer is 40 exponential minus 50t, isn't it? This is the solution. So let's see whether this is indeed correct. So yeah, so this is correct. So the answer is 40 exponential minus 50t volts. This voltage here, it is given by this particular expression here. Fine. Okay. Fine. So yeah. So since there is no one else today in the discussion session, so Jasmine, do you have any doubts? So I was discussing, I guess you were not present at the time that I was discussing that particular question, right? So if you have any doubt, you can ask me.
No, sir.
Okay, fine, no problem. So I will discuss previous week's question, one of the previous week's question. Let's see. Okay, fine. So in week 3, there was a question which I didn't discuss. Yeah, so this is a Thevenin's theorem question. So I want to find out the Thevenin's equivalent between across the terminals A and B. So can you help me in this regard, in this question? So this is week 3's content. Can you please, since week 3 was covered earlier and there was also a quiz on this and solutions are also shared, can you help me find out the Thevenin's equivalent in this case? Can you tell me what to do, how to find out Thevenin's equivalent here across this terminals A and B? Can you help me, Jasmine? Can you please unmute yourself? Okay, fine. So I will be discussing this question now. So in this question we want to find out, the question is find Thevenin's equivalent across terminals B. Fine. I want to find out the Thevenin's equivalent here. So how do I do that? I will first what do I do? So what should be the first thing? So what is Thevenin's equivalent, by the way? Suppose you have a network here and you have two terminals coming out. This is, let's say, A, B. If this is a DC network, so in this case you can replace this particular network DC LTI network. So let's erase this particular. It should be linear network. In that case you can replace this with its equivalent, which is, you can replace this whole network. This network can contain all sorts of things, like there can be voltage sources, there can be resistances, there can be capacitances, inductors and all. So you can replace this particular network with some equivalent voltage source, okay, and some equivalent impedance Z. Fine. So since we are only concerned about DC networks, so we will be, in DC case you have no capacitors and inductors, right? So this and this are gone. So basically for that case you can replace this particular network by a voltage source V and a resistance R Thevenin. This is V Thevenin, this is R Thevenin. This is across A and B, right? So here also we have to replace this whole network this network that is shown here, this network, we have to replace it with an equivalent voltage source like this and a resistance like this. Okay, so how do we do that? So let me bring this guy down. Okay, let me bring this guy down here. Yeah. So how do we do that? So the step one is what? Solution. Step one is what? Find V Thevenin. Right. So how do I find V Thevenin? I first what? Open circuit the terminals, right? So in this case there is no need because this is also already open circuited. So suppose if there was a resistance here, right? So and you have to find out the Thevenin voltage across this terminals A and B. Then in that case you had to remove this particular resistance. You have to open circuit it, fine. So in this case it's not required since it is already open circuit case here, right? So you have to open circuit first. Open circuit the terminals A and B. Now what do you need to do? Now you have to find out the open circuit voltage here, which is the voltage across A and B, voltage VAB, that you have to find out. So what will be that voltage? So this, you see that there is a dependent source here, right? It's a voltage source, dependent voltage source, correct? So voltage source is plus here, minus here. Let's say this is voltage V, some V. So what is this voltage? This voltage is given by V is equal to 10 times I naught, and I naught is flowing here, right? So can you what is the current that is going to flow in this branch, in this particular 4 ohm resistance, in this particular scenario? Can any current flow in this particular branch? So you can see that this particular branch is open circuited here. So if any current is going to flow here, there is no path for it to flow, right? So this current here is 0, fine. So all this current is going to flow like this, okay? The current flowing through this 4 ohm resistance is equal to I naught, right? So I naught is equal to 2 ampere, right? This current here I naught is completely going to come from this particular current source, 2 ampere. The current here is I naught is equal to 2 ampere. So now let me erase this, it's become messy here. Fine. So I naught is 2 ampere. So what is this voltage here? It's equal to 20 volts. And what is the sign of that voltage? It is plus here, minus here. V is equal to 20 volts, right? So this 20 volt is between this and this terminal, fine. So what is the voltage at this terminal? The absolute voltage with respect to the reference here. So this 2 ampere current is going to flow through this 4 ohms, right? So the voltage here is equal to 8 volts, and this the voltage across this terminal, these two terminals, is equal to minus 20 volts, fine. So this node is at a higher potential compared to this node. So going from here to here, I will see a voltage drop, and that voltage drop will be equal to how much? 20 volts. So if this is 8 volts, this particular node will be how much? 8, sorry, this will be equal to 8 minus 20 is equal to minus 12 volts, right? So this node here is at minus 12 volts. So if this node is at minus 12 volts, what will be the voltage at this node? So you can see that the voltage at this node will also be equal to minus 12 volts, simply because the current flowing through this is 0. Since the current flowing through this is 0, there is no voltage drop across this 2 ohms resistance. So whatever voltage appears here, the same voltage appears here. Fine. So VAB, hence VAB is what? It's written here, let me write it here itself. VAB equal to minus 12 volts. So VAB is also equal to V Thevenin, right? So V Thevenin is equal to minus 12 volts. Fine. Now that you have found out V Thevenin, now let's find out the R Thevenin. Find out, fine. Let me drag it down again. It is easier to, let us just copy it, paste it here. Yeah. Now we have to find out step 2 is to find out R Thevenin. Okay. So what is, how do we find out R Thevenin? So first, for finding out R Thevenin, remember that we have to first desensitize all the independent sources. So where are the independent sources in this case? So you can see, first of all, let me mark the reference here. This is the reference. Fine. So the independent source in this case is this 2 ohms. So I will have to open circuit or remove this 2 ohms here from here. This is also a source, but this is not an independent source. This is a dependent source. So we will not be removing this, right? Fine. So in this case the voltage, sorry, the current source is removed, and then we have to find out the resistance in this case between R Thevenin. This is R Thevenin, right? So we have to find out the equivalent resistance between these two terminals. For that, what should we do? We have to connect a voltage source here, and we have to find out how much current it is taking. So the R Thevenin will be equal to how much? It will be equal to V by I, isn't it? Fine. So if there is a voltage source V here, let's say it's equal to 1 volt. So how much current will it be taking? So let's write out the KVL across this loop, isn't it? The KVL will be KVL across the loop. What will be that? Will that be, so it will be equal to 1 volt minus, so let's say this is the I have already said that the current is assumed to be equal to I, and this flowing in this direction. So while going through this across this resistor, there will be voltage drop. So 1 volt minus 2 times I minus, it will not be minus, it will be plus. You see that this voltage here is greater than this voltage, that this node is here is greater than this node, right? So while going from here to here, we have a voltage increase, isn't it? The potential is increasing when we go from this node to this node. And what is that potential increase given by? Is equal to 10 times I naught, right? And what is I naught equal to? I naught is equal to I. So I will just say this is I minus 10 times I, and again from going from here to here, I see that the current is flowing in this direction, and the current flowing through this direction is going to create a voltage drop across this 4 ohms. So this will again be minus 4 times I. This is equal to 0, right? So now let us find out how much is the current. So 2I minus 4I minus 6I plus 10I is 4I, right? So it becomes 1 volt plus 4I is equal to 0, right? So I is equal to minus 1 by 4 ampere is equal to minus 0.25 ampere. Fine. So what is this minus sign denote, by the way? It shows that the current, the direction of current that we assume, which is equal to which was in this direction, is wrong. Okay, the direction of current is wrong in this case. So basically the direction of current is, the current is going to flow in this direction. Fine. but as per our convention we have to assume that the current is going to flow in this direction only, the direction that was assumed earlier, that is in this direction. So for that the current comes out to be minus 0.25 ampere. So what is the Thevenin resistance in that case? It is equal to V by I. What was V? V was equal to 1 volt and I is equal to minus 0.25 ampere, becomes equal to 4 ohms, but with a minus sign. So you notice something very peculiar about this particular question. You see that the Thevenin resistance, it came out to be a negative value. The Thevenin resistance, the resistance is less than 0 in this case. So it is not a surprise. So whenever you have dependent sources in a network, you can very easily get negative resistances. So this is a technique. In fact, negative resistances are basically realized in this manner only. They are not naturally occurring things, so they have to be realized using dependent sources only. Using dependent sources, we do realize negative resistances. Yeah, so finally the Thevenin equivalent will be what? Step 3 is my Thevenin's equivalent. So this will become of this kind, right? So there will be a voltage source, there will be a resistance. This is R Thevenin, this is V Thevenin. And what is V Thevenin equal to? What was V Thevenin equal to? It was equal to minus 12 volts, isn't it? So to minus 12 volts. And what was R Thevenin? R Thevenin equal to minus 4 ohms. So this is terminal A, this is terminal B. So this is the Thevenin's equivalent of this particular network, right? So I will show here. For this network, the Thevenin's equivalent between terminals A and B is given by this particular is given here. So is there any doubt in this question? Do you have any doubt, Jasmine?
No, sir.
Okay, thank you. Fine, so this is what I was going to discuss today. So you have any other doubt?
No, sir.
Okay, fine. So that's all from today. Let's meet in the next session. Fine, thank you.